Okay, I'm really excited to be talking to you today and walking you through how you can use synthetic data sets to facilitate the safe sharing of sensitive data. If you want to follow along with the slides and with the analysis script and with the data, you can access it on that link there, which I've also put in the chat as well. So it's very relevant to be talking about open data when we're talking about reproducibility. And there's a number of benefits, of course, but there's also a number of risks. But in terms of the benefits, open data is super important because it provides an incredible amount of utility for science, society, and the economy. Doing research is incredibly expensive. So by not sharing data, you are potentially replicating what a lot of other people are doing and keeping the data to yourself. By sharing the data, other people can do exploratory research and they can generate new hypotheses. One of the things which a lot of people talk about when it comes to reproducibility in open science is that there is a big focus on hypothesis-driven science, and that's true, but it's very important to understand that in order to get to hypothesis-driven science, we also need to do exploratory science. And by having open data, we can actually do exploratory analysis of other people's work as well. But in addition, with open data, you can also verify other people's analyses too. So there's a number of different benefits when it comes to science, society, and the economy. Verification is super important, and you can also form these new hypotheses, like I mentioned before. But we also have to consider participant privacy. Quite a lot of times when we're having these discussions about open data, a lot of people talk about it as if it's the easiest thing in the world. But that's because they tend to work with data which isn't necessarily sensitive, but a lot of people do work with sensitive data. I know for me, I'm working with a lot of patients with autism, and there aren't that many young people with autism in Norway. So it's quite easy to identify people if you're posting open data. And that could possibly be the case with your work as well. You have data where it's not straightforward to share. So we have a bit of a problem there in that we have this trade-off between what's called disclosure protection, that's protecting the privacy of participants, and also the utility of open data. So there's plenty of benefits for having open data, but at the same time, we need to consider the disclosure protection of our research participants. So very high utility. If we have completely open data, it's a lot of utility. People can use that and ask some very interesting research questions, but there's very little disclosure protection. But if you have complete disclosure protection and closed data, your participants' privacy is completely protected, but there's very little utility there because people cannot access the data. Of course, we have the common line, data is available upon reasonable request, but there was a recent study that came out a couple of weeks ago, which found that very few people actually comply with that. So there needs to be other ways that we can actually share our data while at the same time maintaining participant privacy. So there are a number of approaches that have been done traditionally when it comes to potentially reducing the risk of sharing participant data while also sharing at the same time. You can remove identifiers like names, obviously, addresses and national ID numbers. You shouldn't laugh because it's happened in the past that people have shared these things. Doing this stuff where you're removing common identifiers reduces risk, but it is still possible to identify individuals this way, even with the sort of information which you think is not identifiable. But if you can join the dots together, it can be relatively easy to do this if you're not careful. You can also aggregate sensitive variables. So instead of actually giving individual ages, unless age is a very integral part of your analysis, you don't necessarily have to share specific age as a continuous variable. You can also bin it and do categories like 18 to 25 or 26 to 30 or what have you. So this does somewhat reduce the risk of identifying individuals in your data set, but this is at the expense of data utility because perhaps you have a research question where it is very important to treat age as a continuous variable and you're losing information if you're using it as a categorical variable. Another alternative is adding random noise to the data set. This is something that people have done, but again, people have been identified using this sort of method. So this is not particularly foolproof. So the question is, can we actually increase data utility? Can other people use our data while at the same time also maintaining participant privacy? And yes, there is a solution, and it is called synthetic data. And this is a new data set which mimics the original data set by preserving the statistical properties and relationships between these variables. So we have a compromise between disclosure protection and utility. It's not perfect, absolutely perfect disclosure protection, which I'll get into soon. There are some limitations to consider. And it's not perfect utility because you're not sharing the exact same data set, but it is an extremely good compromise between the two. This works in the same way, in a similar fashion to multiple imputation. So you have a series of variables within your data set. These can be categorical, these can be continuous, and it uses the same variables, except it jumbles everything up. But at the same time, after you've done this, you still maintain the same statistical properties. So if you have an average age here of 40, then in the synthetic data set, that's going to be very close, if not the same as 40. Same thing when it comes to life satisfaction. So the same sort of numbers that you have in the observed or the real data set, you're going to have in your synthetic data set. But what's important as well is that the relationships between variables are also maintained, which is critical for doing exploratory analysis. So not only are the statistical averages and standard deviations and variances very similar, but the relationship between variables is also similar, which is very key if you're doing exploratory analysis on this synthetic data set. So, but the benefits of synthetic data is that you can reproduce the analyses. So you can do your data on a closed data set, which you wouldn't want to share. You can share the synthetic data, and you can say to readers, you can when you're publishing a paper, you can go, hey, due to privacy concerns, legitimate privacy concerns, we cannot share the data. We have shared a synthetic data set, which reproduces the analyses. You're not going to get, in some cases you will, but in a lot of cases, you're not going to get exactly the same results, but you're going to get results which are extremely similar, which allow the people to reproduce your analysis. Other people can explore the data and generate new hypotheses, which is really key. You might not have all the research ideas, but someone might come along going, gee, this person has collected this data, which I'm very interested in, and they can actually do the exploratory analysis on their synthetic data and go, hey, these are some really interesting results. These can form hypotheses for future hypothesis-driven research. So you can explore data that way. And the disclosure risk is essentially zero. Right now, there is no way to possibly identify people under most circumstances as well. So the risk is extremely, extremely low. So we have the best of both worlds. We're able to share the data so that other people can explore the data and verify the analysis, but at the same time, you're maintaining participant privacy. And we're doing this through the coolest named R package. It's called synthpop, which stands for synthetic population data. This was originally created for sharing census data. So most countries have huge amounts of census data, very, very sensitive information with a lot of people, but at the same time, researchers want to get access to this. So one solution which people have done, this is in the UK, the University of Edinburgh, is this synthetic, the idea of synthetic data is not new, but the easy application using this package is relatively new. This package first came out in 2016. It has only been used traditionally for census data. And I was doing a lot of Googling a couple of years ago, and I thought, why is this not done within psychology? This is absolutely perfect. And that's why I wrote a tutorial paper, because I thought this is great. I'm going to use this for my own research, and other people should be using this as well as a way to introduce this to a wider population. So a lot of this part of this tutorial is based on my tutorial paper, but the other part of this tutorial is based on a fantastic tutorial package called Scholarship from the University of Glasgow, which I'm going to link to as well. So that's the example data set we're going to be using, because it's more relevant than the data set that I use, which is very specific for my research field. So we're going to be doing that. But synthpop is an R package which allows you to create synthetic data based on ideas originally proposed in the 90s, but now it's very easy to implement within this synthetic data set package. So for our demonstration, we're going to ask this question, which is relevant to most of us, whether we're students or researchers. What is the impact of motivation and statistics anxiety on academic procrastination? This is a real study which happened in 2014, and the data set that we're working on is a replication of this particular study. So we have a number of variables that we're interested in, looking at academic self-regulation, GSL, or if it's in brackets and in italics, that's the name of the variable within R, or within the data file that we're working with. Intrinsic motivation, statistical anxiety rating scale, stars. That's an interesting one. I'd probably score quite highly on that. And procrastination assessment for students. So a number of different interesting variables that we're dealing here for this particular analysis. Like I said, we are going to be working off this data file, which I've put in the chat. So you can open this up and we have the slides, we have the data, and we have the R script. What you're going to need to do is to download the CSV file and put this into your working directory. But it's critical that within your working directory, you put the data within a folder called data. That's lowercase d data. So download the done/replication CSV and place this in your working directory within a folder called data, because that's what's going to help make this script work for you. So I'm going to give you a little bit of time to go there to this link, which is also in the chat. Then you can have a look. You can download the CSV file and you can get started. Remembering to put this in a folder called data within your working directory. So it's going to look something a little bit like this. Let's open it up here. Yes, we're going to get to that. Yes, we're going to talk about outliers as well. But yeah, so you can see here is my folder structure, and I've set something up called data here. So set up your working directory, import the script which is on OSF, and you can put this within your working directory, and also create a folder called data, and within that put that file here, the done CSV file. Okay, but yes, we will get back to the question of outliers. First thing we want to do is load the packages that we're going to be needing. This is a cool little function that actually checks whether you already have these packages installed, and if not, it installs them for you. So this is the packages that we're going to need. The main workhorse is, of course, it's the synthpop package, but a few of the other packages we're going to be doing, which is mainly for visualization. But the main thing we're going to be using is synthpop. So I'll give you a little bit of time to run that function, which is going to install your packages for you. Okay, and it confirms here that all the packages are installed and ready to go. Next thing we're going to do is to load the data, remembering that this script assumes that your data is inside a folder called data. So the directory is data, or your working directory, data/donereplication.csv. And we're also going to be removing some of the variables or some of the columns that we don't need for the purposes of analysis. So run that, load the data up. Now, one thing when it comes to looking at synthetic data sets is, in order to compare our synthetic data with our real data, we need to compare the results of linear models. And one thing which blew my mind when I first learned it, mainly because I didn't know why my statistics lecturers didn't tell me this, is that most common statistical tests are actually linear models in disguise. This is a fantastic resource that goes through how this is all implemented. Super interesting stuff. But for the purposes of doing this synthetic, comparing your synthetic data, you need to convert, if they aren't already, you need to convert your models, your statistical tests into linear models. And if you're doing conventional statistical like correlations or t-tests or ANOVAs, these can all be converted. So that's one thing, and that's a requirement for what you have to do to use synthpop in order to actually compare the results from your synthetic data versus your real data. First thing we're going to do is fit a linear model. We have our outcome, PASS, and our three predictors, and we're specifying our data, which is real data, and we're also plotting the results. So run this linear model, and we're going to get this particular output here. So this shows us that this particular model explains 18% of the variance. It is statistically significant, and looking at the coefficients, procrastination tended to increase with higher levels of statistics anxiety, or the STARS variable, and procrastination tended to increase with lower levels of self-regulation, which is the GSL variable. So these are the model results here. And this is it. I love this package. This package provides an amazing visualization looking at your linear model assumptions. So running this check model function gives you this, and yeah, things look pretty good. So you highly recommend this visualization. Really, really handy. Looks very, very nice and does all the work for you. So running that, then this is what we get. So we're just confirming, yeah, things don't look too bad for this particular model. Okay, the next thing we're going to do is to restructure our data. So we're going to resave our data as a data frame instead of a tibble, which is what it is at the moment, convert gender to a factor, and also convert degree program to a factor, which is just going to make our life a little bit easier. And then we are going to create a code book for our synthetic data using that function at the bottom there as well. Next few things we have to do in order to reproduce our synthetic data, we should set a seed. So we're setting a seed here, 2018. And for this first demonstration, we're just using two variables. Of course, with synthetic data, you can use, in principle, unlimited, but you can use hundreds of different variables, but the processing will take a lot of time. For this demonstration, we're just using two variables. For the initial demo, we're going to be looking at GSL because this was the strongest predictor in the linear model that we just fit. So then what we're going to do is we're going to save this synthetic data using the reproducible seed from above. So the syn function, SYN, is what creates our synthetic data set, and we're going to be using the seed that we specified, and we're going to be saving that. Now, I mentioned before that there are some risks under some circumstances when it comes to sharing your synthetic data sets. And one is that if by chance your data set happen to replicate a real data set, this can reduce participants' trust if they recognize themselves in the data. If you have a small amount of participants and a small number of variables, the chances of you by chance replicating an original participant's data can be quite high. So if you told a participant, hey, we're going to be sharing your data, it's going to be synthetic, no one's going to tell it's you, and then they look at the data again and then they figure out, well, that's me, they're not going to have much trust in the data and not going to have much trust in research. You can get into a few problems. So you need to check that you haven't replicated any particular individual so that a synthetic individual isn't the same as a real individual. So by using this command, you can remove any replicated uniques, which is a replicated like a synthetic person that replicates a real person. And another recommended approach is to add a fake data label. So for instance, say this data gets out there in the wild and somebody finds this going, wow, look at this real data. I'm going to publish on this real data. It's not real. You can't publish based on this synthetic data, although you can generate new hypotheses based on this data by working with the original authors, which we're going to get back to. Doing this is just an extra stop that people don't think it's actual real data. So it's just another thing that you can do. Okay, so then you run this and then you can save the synthetic data set with these removed uniques if there's anything. So this is to completely remove the risk of anyone being identified. We're actually gone through, and of course, when you have two variables, the risk of this happening is quite high. But when you're working with a typical data set within the biobehavioral sciences where you have, 60 individuals and you might have 10 different variables, it's the chances of you having a replicated person is quite low, down to like sort of 1% with typical 1 or 0% with typical data sets. But you have to check this. Make sure you check this. There are two types of utility that you want to check for your open and synthetic data. One is called general utility, and that there is overall similarities in the data set. So if you had, people with a high school education versus no high school education, and there was 50 in one group and 20 on the other group in your original data, you want to make sure that things are quite similar in the synthetic data set. The second thing to look at is specific utility, and that is how similar are the fitted models between the synthetic and original data sets. So if your research question is how much are these two variables related, you want to actually look at are the results for that, is it the results for that research question similar between the original data set and the synthetic data set. So to do this and to check the general utility for the relationship between the PASS and GSL variables, we can run the command function, and you just specify the synthetic data object, the original data which you made, the synthetic data which you made, the original data, and there's an option there for how you actually want to present, whether you want to present counts or percents. So here we can see in dark blue, we have the observed or the real data, and in light blue, we have the synthetic data. And of course, the numbers are not exactly the same, but they're quite similar between the two. So it's a good eyeball check just to make sure that the synthetic data set has roughly the same characteristics as the synthetic data set for these particular two variables that we're working with. Now, let's check the specific utility of our model by running a linear model equivalent in our synthetic data. So using the same sort of structure that you do fit a linear model within R or within base R, we also do this for the synthetic data using the lm.syns function. And then we compare the original, we compare the synthetic model with the original model. So we get a statistical test. And for this particular statistical test, this was not significant. So this provides evidence or points to evidence that these two models are equivalent. And eyeballing the two models here, we can see there's a very, very high degree of crossover between the synthetic model and the observed model. The coefficient estimate is almost exactly the same, and the confidence intervals have a very high degree amount of crossover. So looking at our synthetic data, we're very confident that this gives almost the same results as our observed data as well. So we have a statistical output, but we also have a visualization. So if you were sharing your data using a synthetic data set, this is something you might include in your supplement. We can say, hey, we'll share the synthetic data, and here are the statistics for how this data performs, and that this data is almost identical. So you can run the same sort of analysis and get similar outcomes between these two models here. Okay, so we've just done a demonstration with two variables. Now let's have a look at doing this with the full data set and looking at its general utility. So we're going back, we're returning to the original data, and we're using the same seed as before, and we're going to compare the original data with the synthetic data, which we just created above, and we're going to have a look at the general utility. You might need to press return to see all the plots in the output in R. If you do, you'll get a prompt in R to do this if needed. So it'll only show you 4 at a time for when it comes to the plots, and then it'll only show you the output when it's showing you the final set of plots as well. Looking at this, we can see that again, it's very, very similar between the two, between the observed and the synthetic. It's done a very, very good job at creating the synthetic data sets in terms of the actual variables, or the 7 variables that we're working with here as well. So that's nice. Eyeballing it, we can say, yep, these things are pretty similar between the two. We have to create, again, a second linear model using the full 3 predictors here. So this is exactly the same as the first linear model that we fit, except we're doing it within the synthetic world. And then we're comparing these two models here. Looking at our stats, it didn't perform as well. You would still say that these are equivalent because or you could say there's evidence towards equivalence because the p-value is not statistically significant. And looking at these particular, looking at these coefficient estimates, some perform better than others. There still is a high amount of crossover between these, but it's important to note. So this is why you would report the output of this going, hey, if you do want to try and replicate this, note that some of the coefficients didn't perform as well as others, but it still is to the level that you're going to get a rough approximation if you're going to be comparing. But it's not as strong as the first model that we looked at. So this is why it's important to share this kind of information, or to share the statistics for your synthetic data creation. The final thing we want to do is to check for replicated uniques. So remember how I said that when you have a high number of participants and a high number of variables, particularly continuous variables, the chances of having replications within your data set is quite low. In this example, we ran this particular command looking at replicated uniques, and there was none in this particular example. So it's important to check that. Look within your data and check that there's no replicated uniques so that you can safely share your data. Well, I've done some simulations as well, and specific utility is maintained when you're looking at a range of different data set types in general. Of course, you need to check this with your own data. I ran a few simulations looking at no missing data and no skew, and different degrees of missingness and skewness. And generally speaking, it works quite well. In terms of outliers, we had a great question before with outliers. If you have a couple of outliers, the synthetic data set will replicate those outliers, but it's important to consider as well is that's another way that individuals can potentially be identified. So if you're working with a data set, for instance, of a small population within Norway, and one person in your data set is 80 years old and everyone is 40 or younger, this person will be identified within the synthetic data set. one strategy around this, it's not ideal, but it's one way around it, is to bin your variable. So instead of actually treating A as a continuous variable, you would say, you know, people who are 35 and up and older, then you would hide that outlier as well. If you have a couple of outliers, that's okay, because at least those individuals can be sort of hidden within those outliers. But synthetic data does a really good job of also recognizing those outliers, but at the same time, that is one way that individuals can be identified. So think very carefully, especially if you have a single outlier in your population. If you want to keep them unidentifiable, I would actually remove them, or you would bin them as a continuous variable, or say they're already a categorical variable, you would sort of include them within another within another variable as well. So think about that when it comes to this, to maintaining the privacy of your participants. Of course, this is a solution if you don't have permission to share data from your participants. But one thing that's easier is actually to ask them. Ask your participants at the outset whether they want their data to be shared. A lot of people are okay with this. You can actually say, if we remove all your identifiable information and we're just presenting these variables, are we okay with sharing your data? Of course, you need to get permission from REC or your local institutional review board to do this and ask your participants. But people are more willing to do this than we think if you ask them. Especially people who if you're studying a particular disorder, they want to be able to improve research on this particular disorder, or people, or under many circumstances, if you ask participants, they're actually very, very interested in sharing data. But the most important thing is to ask them in the first place. And this is a much easier solution than getting synthetic data, is thinking ahead and planning ahead. But a lot of us, I recognize that research takes a long time. It can take years. So you may have not have thought of this when you were designing your research a couple of years ago, for actually asking your participants whether you can share their research data. So synthetic data can help solve two of the most common and valid objections to data sharing. So one is, of course, we need to protect participant privacy, and this is a valid objection. This is very important to consider. We need to have the trust of our participants, otherwise we're not going to have people participating in our research. With synthetic data, we can now create a version which replicates the original results, while at the same time making sure that nobody in your data set can actually be recognized. Now, another common objection to data sharing is this: well, we've spent a lot of money and a lot of time collecting this data, and I've got 3 other PhD students in my lab who want to analyze it. I want them to analyze it first, before other people can actually analyze it. Less valid, but still a valid objection. With synthetic data, what you can do is you can share your data, and other people still can't publish based on your data, because it's not real, it's not synthetic. The only way they can do this is by working carefully hand in hand with you. They can say, hey, we did an analysis of your data. We've got some really interesting results. We'd like to verify them based on your real data. Let's work together and let's collaborate. So doing this almost forces people to collaborate, and you're going to get co-authorship and get the credit that you deserve for collecting your data. People can run the analysis on the synthetic data set, and they can actually send you their analysis script, and you can quickly run that on the original data. You can go, yeah, hey, we replicated this. This is great. Well done. Let's work together. So by doing this gets around this idea that, well, I don't want to share my data because there's still work I want to do with it, and I don't want other people to use the hard work that I've done for my data, which is sort of, I'm not sure if I completely agree with that, but I can understand where people are coming from when they say that. So importantly, we have this real great strength of synthetic data that we can have the same utility of completely open data while still maintaining disclosure control. In terms of utility, open data is always better, because you're going to replicate things exactly, and you're working with the original data. But a synthetic data set is always better than no data at all. It also makes it easier. The amount of times me as a reviewer, I'm looking at a paper and I'm like, I have no idea what they've done. And if I had, even if I had the synthetic data, I could at least have some clue of how the data was treated. So this makes things a lot easier in terms of having your work evaluated. So some limitations: for some data sets, you might not be able to generate a synthetic data set with acceptable utility. Under some situations, this is going to happen. If you have a really small number of participants and a small number of variables as well, and if they're categorical variables, there's a chance it might not do a good job with this. That's why it's important to check both the general and the specific utility. For now, you can only directly compare linear models. So, I mean, it's not a huge limitation, but it takes a little bit of extra time to actually convert. It can take some extra time to convert your analysis into a linear model in order to check your specific utility. And the risk of disclosure can increase under some circumstances if you have replicated uniques or if you have a few outliers in your data sets as well. So those are some limitations there. If you want to go through and do another tutorial with a different data set, which some of this is based on, you can look at this eLife paper, and the data is and the script is online. You can actually run this within an R browser, within your web browser, within R. It's a cool little feature, so you can actually replicate this analysis yourself and use this with your own data. I also want to acknowledge that a lot of this was based on this fantastic tutorial from the scholarship set of tutorials. So there's an intro, and the first one is on creating synthetic data sets. So the data that was used, which was the replication data, and a lot of the script was based on that, which is fantastic work that's been done from the School of Psychology at the University of Glasgow. So I just want to give a shout out to the team there who do a lot of great work. But yeah, you can check all those things there. But yeah, have a look through this eLife paper, which talks a little bit more about the background about how synthetic analysis works. This is done using oxytocin data, open oxytocin data, looking at the effects of oxytocin on cognition, and it just walks through how to do that, and also has some simulations and how outliers are dealt with as well. So yes, let's chat. If you have any questions, we can go through that. But I hope this has been useful, and we'll take questions here and also online as well. So thank you all.